represents the number in that system. Let us see the another system, hexadecimal system. Now hexadecimal system have the base of 16. The digits used to represent the hexadecimal digits are 0 to 9 and A to F. So total number of digits are 16. The largest value of the digit is F. The position weight is therefore multiple of power of 16. As shown in the example, here the digits are shown 0 to F and their corresponding value is 0 to 15 in decimal, whereas the representation in hexadecimal is 0 to 9. After that, A, B, C, D, E, F. These are the hexadecimal representation, and corresponding decimal notation will be shown here as 0 to 15. A typical number system now shown by the same diagram again. The radix point is now called hex point. The left side of the hex point is the integer portion and right side of the hex point is the fractional part. The leftmost digit is called MSD, most significant digit, and the rightmost digit is called as least significant digit. Now if you see the position 0, that is the first position of the integer portion after the radix point on left hand side is 16 to power 0 because base of the system is 16. The first position have the position value 16 raised to 1. The second position have the position value 16 raised to 2 and so on. To the right side of the radix point, that is the fractional portion, the weight of the first position is 16 raised to minus 1. Second position is 16 raised to minus 2. Third position is 16 raised to minus 3 and so on. A typical number system shown in the table, the digits are increasing from 0, 1, 2, 3, 4 up to F, and after F, the MS digit will be incremented and lower digit will be resetted. So here if you see, the MS digit is 1 and lower digit will be resetted at 0. So again 1, 0, 1, 1, 1, 2 up to 1 F. When the last digit becomes F again, the MS digit is again incremented, that is 2, and LS digit will be resetted to 0. And again LS digit is changing from 0 to F. Again same thing is repeated in the third, fourth column. The MS digit will be incremented to 3 and LS digit will be resetted. So we will see the hexadecimal table continues to multiple digits values. Here only 2-digit hexadecimal representation is shown in the table. Now let us see the conversion of the number system. Any number system to decimal number system that can be achieved by summing all positional values into position-wise weights. Now position values are the digit values given at that position, and position weight is basically the weight of the system at that position. Take an example, binary to decimal conversion. The number given in binary, which is shown here 1011.01. We have shown the subscript 2 here, which indicates that it is a binary number. That is the way to represent the binary number. In many literature, this will be dropped, but the right convention is to add a suffix 2 to represent the binary number, which we want to convert to equivalent decimal number. So we have written the binary value here 1011, then binary point and 01. This is the input value given to us. We need to convert it to the decimal equivalent. We know the weight of the binary system or base of the binary system, that is 2. So position 0 have the weight 2 raised to 0. Position 1 have the weight 2 raised to 1. Position 2 have the weight 2 raised to 2. Position 3 have the weight 2 raised to 3 and so on to the left side of the binary point. That is the integer portion. So therefore here at 0th position in the integer section, we will see the total weight of this 0th position is 1 into 2 raised to 0. That is 1. The first position, the binary bit is 1 and the weight is 2 raised to 1. So therefore the weight of this binary digit is 2. Third position, the binary digit is 0, weight is 2 raised to 2. So 0 into 2 raised to 2 is 0. The third bit, that is the most significant bit, MSB or MSD you can call it, 1 into position is 2 raised to 3. 2 raised to 3 is 8. So therefore the weight of this 1 in MSD position is 8. Add the total individual position weights, 8 plus 0 plus 2, that is 10 plus 1, that is 11. So total binary integer portion have the decimal value 11. Now consider the binary weight. Right side to the binary point, that is the fractional portion. The first position here have the weight 2 raised to minus 1 and the digit here is 0 into 2 raised to minus 1, that is 0. Here there is a typo mistake. Let us correct it. Okay, I have corrected it. So the first position have the position weight 2 raised to minus 1. So 0 into 2 raised to minus 1 is 0. The second position digit is 1. 1 into 2 raised to minus 2 is 0.25. So 0 plus 0.25 is 0.25. So therefore the number 1011.01 binary is corresponds to 11.25. Let us see the example of octal to decimal conversion. Let us see the number given is octal number 358 and 8 here as a subscript, that is indicating the octal number. So 354 octal into decimal conversion. So we have written the number 354, that is in octal. The position values, as usual, only integer portion is given here. The 0th position is this last digit 4. 4 into 8 raised to 0, that is 4. Second, the first position is 5. 5 into 8 raised to 1 is 40. The second position digit is 3. 3 into 8 raised to 2 is 192. And therefore corresponding value, add all these 3 values, that is 236 decimal. So 354 in octal corresponds to 236 decimal. Let us have another example, octal into corresponding decimal number with a fractional value also. So 365.25 octal is converted to corresponding decimal number. So let us see the octal point now. The zeroth position is 5. 5 into 8 raised to 0, that is 5. First position is 6. 6 into 8 raised to 1, that is 48. The second position is 3. 3 into 8 raised to 2, that is 192. So decimal portion, as usual, 192 plus 48 plus 5, that comes out to be 245 here. Now, to the right side, the fractional portion. The first position is 2. 2 into 8 raised to minus 1. 8 raised to minus 1 is the positional weight. And therefore, the first position digit weight is 0.25. Whereas the second position digit is 4. 4 into position weight is 8 raised to minus 2. And that comes out to be 0.03125. Add the 2. So therefore, you are getting the value that is equal to 0.28125. So 365.24 octal corresponds to 245.28125 decimal. Let us see hexadecimal to decimal conversion. On the same track, we have 4C8.2 hexadecimal into equivalent decimal number. We have written now here the hex value. The hexadecimal point is also shown. Now the zeroth position is the digit 8. Corresponding positional weight is 16 raised to 0. So 8 into 16 raised to 0, that is 8. The second position digit is C. The corresponding decimal value is 12. So 12 into 16 raised to 1, that is the positional weight. So it comes out to be 192. The third digit is 4. So 4 into the positional value, that is second position, 16 raised to 2, that is 1024. Add these three individual positional weights, you are getting the integer portion of hexadecimal value corresponds to corresponding decimal value of this hexadecimal integer, that is 1224. Now let us see the fractional portion. The first position is digit is 2. The weight is 16 raised to minus 1. So therefore this comes out to be 2 into 16 raised to minus 1 is 0.0125. The second digit is 4 into 16 raised to minus 2. So therefore the positional value, digit value is 0.015625. Add the 2, you are getting the fractional portion in the decimal. So therefore here the last column indicates the hexadecimal value and corresponding decimal value. You also note here that the subscript H is shown here, that is indicating the hexadecimal digit, and D indicate the decimal digit. So instead of 10, D can also be used. Now conversion from decimal system to binary system or octal system or hex system. The decimal to binary conversion is also known as double method of conversion. The decimal to hexadecimal conversion is also known as hex double method of conversion. In these methods, we are converting the integer portion and fractional portion separately and then attaching. Let us see what is the double method. In double method, let us say decimal to binary conversion, we will continuously divide the number by base and note the remainder, and list the remainder values in reverse order, that is from bottom to top. Let us see the example. Here the number given is 105 decimal and we want to convert it to binary. So base of the binary system is 2. So we will continuously divide this number by 2. First time divide by 2. So you are getting quotient 52 and remainder 1. Then divide this 52 by again 2. You are getting quotient 26, remainder 0. Then this 26 will be divided by 2 again. You are getting quotient 13, remainder 0. Then 13 will be divided by 2. You are getting quotient 6, remainder 1. Then 6 will be divided by 2 again. Quotient will be 3, remainder will be 0. 3 will be divided by 2. Quotient will be 1, remainder will be 1. Again 1 will be divided by 2. You will see the quotient will be 0 and remainder will be 1. After this, when the digit reaches to 0, we have to stop the division. Once this division is complete, go on writing the binary reminders from bottom to top, as bottom digit or bottom reminder is MSB and top reminder is LSB. So therefore 105 decimal will be converted to 110101 binary as shown here. So what we have done? We have taken the number, continuously divided by 2 and note the remainder. The first reminder will be LSB and the last reminder will be MSB, and the division process will be automatically stopped when quotient becomes 0. On the similar track, if you want to convert decimal number to octal number, now what is the base of octal system? That is 8. The number given is 204 decimal. Now we are going to divide it by 8. So 204 divided by 8, the quotient is 25, remainder will be 4. Again 25 will be divided by 8, quotient will be 3, remainder will be 1. Then 3 will be divided by 8, quotient will be 0, remainder will be 3. After this the process will stop because 0 divided by 8 again, that is the base of the system, will 0 itself. And therefore we got the end of the conversion process. After this, whatever the last remainder we are getting, that is most significant digit, and the first remainder will be least significant digit. So we are writing the reminders from bottom to top. Bottom will be MSD and first remainder will be LS digit. Similarly, decimal to hexadecimal conversion. Here again in this method, we will see the number given is 259. Our method is we are dividing it by 16. The base of the hexadecimal system is 16. So 259 by 16. the quotient will be 16 and remainder will be 3. Then this 16 will be divided by again 16, the quotient will be 1 and remainder will be 0. Again 1 will be divided by 16, quotient will be 0 and remainder will be 1. Now write the reminders from bottom to top as MSD to LSD. So 103 will be corresponding hexadecimal number, corresponds to the decimal number of 259. By using this logic, we can convert the various numbers and tabulate some basic combinations in the table shown here. So you will see, first column indicates the decimal numbers, second hexadecimal number, corresponding binary number in the third column, corresponding octal number is shown in the fourth column, and the binary combination corresponds to this octal number is shown. Decimal 0 corresponds to hex 0 up to 9. The hex number and decimal numbers are same. In decimal number after 9 it will be incremented to 10. Whereas hexadecimal number have total 16 symbols. So next symbol will be A, then B, then C, then D, then E and F. So therefore F corresponds to 15 decimal. The corresponding binary value will be from 000, 1 will be 001, 2 will be 010, 3 will be 0010, 4 will be 100, 5 will be 0101, 6 will be 0110, 7 will be 0111, 8 will be 1000, and 9 will be 1001, 10 will be 1010, and so on. So F will be 1111. Corresponding octal number up to 7 the numbers are same. After 7 the last digit will be resetted and next digit will be 1. So 8 corresponds to 10 in octal, 9 corresponds to 11, 10 decimal corresponds to 12, and 15 corresponds to 17 octal. The octal number is normally have only 7 digits, and to represent the 7 combination in binary only 3 binary digits are required. So 0 corresponds to 000 and 7 corresponds to 111. The next digit octal representation in binary form is 001, 000, that is 10. 10 is the first octal number is represented by 3-bit binary, and second octal combination will be represented by next 3 bits. So 10 in octal will be represented by 6 digits in binary. So likewise the digit 17 in octal will be represented as 001, corresponds to this MSD, and 7 LSD will be represented as 111. These combinations, decimal, hexadecimal and binary, you need to remember because these are required many number of times further in the subjects of digital electronics. Now let us see the fractional part conversion to binary. In this process, what we will do is, instead of division, we will use the successive multiplication of the fractional part. Multiply only fractional part successively by base and note down the carries. Let us see the example. Now decimal fraction to binary fractional number can be converted like this as shown in the figure. Let us convert the decimal number 0.42 into binary. So what is our logic? We will take a fractional portion given, that is 0.42. The base of the binary system is 2. So 0.42 into 2, 0.84. Here no carry is generated, C carry is 0, and therefore it is noted as 0. Take the fractional portion again, 0.84 multiplied by 2. Here after multiplication we are getting the product 1.68. So carry is 1 and fractional portion is 0.68. So fractional portion will be continued in the successive multiplication and corresponding carry will be noted down. So similarly this process will be continuously going on, and once the process stops we will note the carry. The last carry will be considered as the LSB and the first carry generated will be MSB. Here this process shown in 5 steps, but 6 step is also present, 0.44 into 2 again. Then whatever the remainder again you can go on multiplying by 2. But ultimately the last carry will be always LSB, and LSB values are very least significant, and therefore after decimal point the rightmost value, that is LSB value, will be ignored and truncated up to significant digits only. So here we will truncate this value up to 5 binary significant digits, and we will stop the process up after 5 steps. So therefore 0.42 decimal portion, this is the fractional part, is corresponds to the binary fraction 0.01101. Let us take another example. Convert the number 0.6234 to XXX8 shown here. So indirectly they are asking us to convert this fractional portion to octal number fraction. Again the process is same. We have to successively multiply by the base of the system in which you want to convert. We want to convert in octal, and therefore base of the system is 8. Take the fractional portion again, whatever given, that is 0.6234 multiplied by 8, you are getting the product. From the product the carry portion is taken out and fractional portion remains as it is. The fractional portion is in the next step taken and multiplied by 8 again product is generated. The carry portion will be noted down, here it is 7, and fractional portion is continued in the successive multiplication. Continue this process up to known number of significant position or required number of significant position, because this process will be indefinite. So if you want 4 number of significant digits, then only 4 steps can be performed. If you want 5 digits after decimal point, then 5 successive multiplications can be performed, and so on. So we have noted the carry from the first multiplication, that is 4, and carry from the last multiplication, that is 3. The last carry will be noted as LSD and first carry digit will be noted as MSD as shown, and therefore the decimal portion 0.6234 will be converted to the fractional part in octal as 0.47713. Now decimal to hexadecimal conversion, the fractional portion of hexadecimal, fractional portion of decimal part is converted to the fractional portion of hexadecimal system. Again logic is same. Whatever the fractional part given, that will be multiplied by the base of the system. The base of the system is, it is a hex system, therefore multiplied by 16. Then in the product, remainder, that is carry will be noted, and remainder will be, or fractional part will be taken in the next successive multiplication. Again product will be generated. Here 15 will be carry over and 0.234 is the remainder portion. fractional part. This fractional part will be taken again and multiplied by 16 again. So you are getting the product 3.712. So 0.712 is the fractional part taken in the next successive multiplication, and the carry will be noted down. So continue this process up to the required number of significant digits required in the fractional portion. We have continued up to 6 digits and then we stop. Once the process is complete, the first remainder will be treated as MS digit and the last remainder will be treated as LS digit. So go on writing the digits from MSD to LSD from left to right after the decimal point as shown. So the number becomes 0.11 decimal equal to 0.1 F3B64H. This way the hexadecimal conversion can be done. Now we will see the conversion of mixed decimal number to any radix. Mixed decimal number means what? The integer as well as fractional part is given and you have to convert it to other number system. For example, here decimal to binary conversion. Here decimal number given is 49.25. We need to convert it to the binary number. So what we do? We will take integer portion separate and fractional portion separately we are going to convert. The conversion logic for integer portion is we are successively dividing the number by the base of the system and remainder we are noting and then taking the remainder from last remainder as MSB from bottom to top and the first remainder as LSB. Whereas in fractional portion what we do? We will do the successive multiplication by the base to the fractional portion of the given number, that is decimal number, and note down the carry. Continue the successive multiplication up to the required number of significant digits in the required fraction of hexadecimal number or octal number or binary number. And then whatever the reminders we were getting, whatever the carry position we are noting down, we are writing it. The first carry will be MSB and the last carry will be LSB. So 49, we will see here, we will take the integer quotient, 49 by 2. Quotient will be 24, remainder will be 1. Again 24 will be divided by 2, quotient will be 12, remainder will be 0. 12 will be divided by 2, quotient will be 6, remainder will be 0. 6 will be divided by 2, quotient will be 3, remainder will be 0. 3 will be divided by 2, quotient will be 1, remainder will be 0. 1 will be divided by 2, quotient will be 0 and remainder will be 1 and the process stop here. So we are getting the column here. The last remainder is MSB and first remainder is LSB. So 49 decimal corresponds to start writing the MSB to LSB from left to right. So this is 100001. So here the first digit is MSB 10001. So the integer portion we have converted to the binary corresponding value. Here in step 3, you will see the fractional portion. What is the logic of converting the fractional portion to other number system? Take the fractional portion, multiplied by base. Then the product will be generated. From that product, carry will be separated out and noted, and only remainder will be continued in the successive multiplication process. So here in the first step, the product is 0.25 into 2 is 0.5, carry is 0, we noted it, and 0.5 will be taken in the next step. Again multiplied by 2, you are getting 1.00. So carry is 1 and the fractional portion is 00. 00 will be multiplied by 2, process will be automatically stops. So here you are getting the first carry, that is 0, that is MSB, and the last carry as LSB. Go on writing MSB on left hand side and LSB on right hand side. Now see the decimal point. From decimal point, the MSB will be first carry, that is 0, and the LSD, least significant digit, will be the next carry. So 0.01. 0.25 decimal corresponds to 0.01 binary. So therefore, the total number 49.25 decimal corresponds to 11001.01 binary. This type of examples may be asked in the examination for 5 to 6 marks. The another example, decimal to octal conversion. Now try it yourself. Let us see. We have the decimal portion, integer portion of the decimal number is 3000 and the integer portion is 0.45. As usual, we will take decimal separately, the integer portion separately and fractional part separately converted. So take the integer part of the decimal. We need to convert it to octal. So base of the system is 8. So successively divide the integer portion by 8. So here we are dividing the integer portion by 8 and successive quotient will be divided by 8 till the last quotient will be 0. And each step, whatever the remainder comes, we are noting down. The first remainder will be least significant digit and last remainder will be most significant digit. So we will write the digits from the remainder column from bottom to top. And therefore 3000 corresponds to 5670. So it is shown here. Now take the fractional part. In the fractional part, what we are doing? We are taking the fractional part and successively multiplying it by the base of the system, that is 8. So 0.45 into 8, that is 3.60. So carry will be noted as 3 and the fractional part remains 0.60. Take this second fractional part 0.60 multiplied by 8, it will be 4.80. 4 will be the carry and 0.80 will be the fractional part that is taken in the next successive multiplication step, and this will be continued up to the required number of digits. We have stopped this process after 4 steps and we got here carry. The first carry will be most significant digits of the fractional portion and the last carry will be the least significant digits of the portion, and therefore see the decimal point. After decimal point, MSD will be 3, so we have written 3, then 4, then 6 and then 3. So therefore 0.45 decimal is equivalent to 0.3463 in octal. Combining, last step will be combining decimal, this integer part and fractional part. So 3000.45 decimal will be 5670.3463 in octal. So this way you can convert the numbers from one system to another. In the same theme, we can convert decimal number to hexadecimal number. Again, if the number is given as a combination of integer value and the fractional value, then integer value and fractional value will be separately converted, and then the converted integer and fractional value will be combined. So here the decimal integer value given is 2003 and fractional value will be 0.31.
As usual, we know in integer part conversion, we are successively dividing the number by the base of the system. We need to convert it to hex system, and therefore we successively divide it by 16 and noting the reminders. Every subsequent quotient will be again divided in the next step till the last quotient will be 0 and the remainder will be noted. Once the remainder is noted, we will write down the value of the remainder column from bottom to top. So bottom will be MSD and the first remainder will be LSD of the integer portion. So therefore, here 7, 13 corresponds to D in hex. So 7D3 will be the integer portion. In the fractional portion, the logic is again same. Fractional part is taken and multiplied by the base of the system, that is 16. Carry is noted down and fractional part is taken in continuation for next successive multiplication step. Go on doing this and noting the carry. And this can be continued up to required number of significant digits required. The first carry generated in the first multiplication is most significant digit of the fraction, and the last carry will be least significant digits of the fraction. So write MSD first after the decimal point, that is 4, say 0.4 here. Then this 15 corresponds to F. So 4F, 5, 12 corresponds to C and 2. So 4F, 5, C, 2 will be the fractional portion. Combine the integer portion and fractional portion now. So 2003.31 the decimal is corresponds to 7D3.4F5C2 in hexadecimal. So we'll stop here, friends, today. We will continue this unit in the next subsequent lecture. Till then, bye bye.